This next presentation is by Anita Nikolich. Anita is a program director for cybersecurity in the Division of Advanced Cyber Infrastructure at the National Science Foundation. Anita is going to be presenting on funding innovative network and cybersecurity research. Take it away. A little short, so I promise.
So my presentation is going to be a little different. I also have a cold, so I'm going to try to speak up, and I tend to speak really quickly, so stop me if you want to hear something that I'm speaking really fast about. So my background is operations. Prior to the National Science Foundation, I was at University of Chicago. Prior to that, I was at Aon, a big insurance company enterprise, and prior to that, I was at WorldCom. So I've kind of seen the span of networking. Now I've taken a step back from day-to-day operations, and I'm looking more at the research angle. And I'll tell you a little bit about, I want to take it above just the networking and kind of tell you a little bit about how networking fits into science and how a lot of science is now done. So the NSF, where I work, is a funding source for 24% of basic research conducted by America's colleges and universities. In fields like math and computer science, NSF's the major source of federal funding for that. So our budget just for next fiscal year is $7.7 billion. Some of the trends for US research, and by this we mean scientific research, are the changing practices of science. There's a lot more global science. It's data intensive. There's complex data flows for the Large Hadron Collider, which resulted in the discovery of the Higgs boson, which got the Nobel Prize, that discovery. Generally, on those type of experiments, there's 2,000 to 3,000 scientists that work in tandem around the globe with very large flows. So that's a really different kind of network that one needs to support from a typical financial enterprise network. So I'm within the Computer Science Directorate at the NSF. The Directorate of Computer Science funds what the internet's going to look like in 20, 25 years. Those are the kind of research projects that are funded. The mission of that directorate is to uphold the nation's leadership in computer information science. So these are some of the national priorities that we try to satisfy for computing frontiers. Everything from broadband access to universal connectivity, sustainability, healthcare, cybersecurity, Internet of Things, workforce development, all those things. So I just wanted to tell you some of the, just to give you kind of the things we deal with every day and that we need to support via a scientific network. One of the big initiatives that was announced 2 years ago now is this BRAIN initiative. And this is to look at basically trying to map the human brain. And just for this fiscal year, this is a $144 million project. And it's trying to develop innovative neurotechnologies to monitor and analyze brain activity, develop new tools, approaches, theories, look at relationships among neural activity, cognition, behavior, trying to solve problems like Alzheimer's, autism, things like that. So when you think about just the density of information that needs to flow across the network, I'm just trying to give you a sense of what that looks like. This is a big project that is coming up for next year with the National Science Foundation. And right now there's a project around food, energy, and water safety and security. We're expanding that. We always have these cute acronyms. This is called Infuse, and it says partnership to really think about the supply chain for water, food, and energy, and to optimize these systems that really, this critical infrastructure of our nation that hangs together. How do you secure and protect that chain so that if there's something in the water supply that's tainted, that doesn't affect a large population? Jeanne, I'm going to skip right to one of the big investments in the future of the internet. So some of you may have heard of Jeanne. It's more an experimental technology. This has allowed researchers to build at scale, they call it a virtual laboratory for networking experimentation. To do this, there's Jeanne racks of equipment in campuses throughout the US. A couple of concepts for Jeanne are sliceability of the network and programmability of the network. So you can have a slice of the network. It's almost like an SDN concept. And you get a piece of the resources of all the computers and switches across that network. The control of the network is programmable, so you can try radical ideas for routing, addressing, naming across the network. Some of the uses of this, for example, one that we just had a really interesting demo of is if there's a hurricane approaching the coast, these folks at University of North Carolina, they have these storm surge models. And when they see a hurricane approaching, they need at a really moment's notice to be able to grab a whole lot of compute cycles. They have a supercomputing center, it's not enough, because they want to get really granular information about where it's going to touch down, how it's going to affect people, how it's going to affect transportation patterns, so they can at a moment's notice program and get a slice of a network and use a bunch of resources across the US to enhance that predictive algorithm through their simulations. US Ignite, that's a program to build some, it's basically stitching together broadband islands across the US to do interesting applications such as the hurricane modeling one. So I'm within the SI's Directorate. I'm in the division called Advanced Cyber Infrastructure. That's relevant because we have we kind of are the bridge between pure research and operations. We like to accelerate the pace of discovery and innovation by doing a few things. We provide high performance computing. So we have, and I'll show you a slide, we provide the supercomputing centers, petascale computing, soon to be exascale. That's going to be through the Department of Energy, but this is really large scale computing. I mean, down at UIUC, they built a whole entire building just for the computer there. That's how large these things are. And the new exascale computing needs 30 megawatts just to run that computer. So that's kind of the scale of it. The data that's associated with it, the networking and cybersecurity. We talk about 1 gig, 10 gig. We're at the level where many, if not most of our campuses have 40 and we'll be getting 100 gig, especially the larger universities. That's just needed these days. And then software to tie it all together. So again, just to give you an idea of this, there's a whole data center at UIUC built just for blue waters. This is for petascale computing. It advances large-scale computational science, and it entailed 5 years of collaborative activities from building the building to the network infrastructure, the data infrastructure, and then getting people to come onto the computer. There's over 100 people that use it every day. I want to talk a little bit about NEON. Again, these are just kind of things that you may not touch in your day-to-day life, but what's really interesting about NEON is it's designed to advance basic ecological theory and transform ecology into a science that predicts things like, for climate science, how can we look at the consequences of human change to the environment? So what NEON does is, you'll see that kind of three-tiered model there. They have a combination of, they're doing aquatic sampling, terrestrial sampling, and then there's airborne aircraft to do sampling of the air quality, carbon dioxide and different things in the air. And they want to look at, so part of that is considered citizen science because people can go out with their smartphones and take pictures of things and different types of sensors. But bringing that all together and looking at how that's brought back to a computer, that's a huge networking challenge. There's literally towers that are in the middle of the prairie, then there's people on their smartphones, and then there's airborne sensors. And they're trying to bring all this information together, infuse it, and figure out how this impacts land change use and what we've done to affect the environment. LSST, again, something you probably won't encounter in your daily life, but it's a very interesting project. It actually won't be online for another 6 years. But LSST, synoptic means camera. So it's a telescope that's being built that they just started last year. It's a telescope being built in Chile, and there's a couple parts to it. It's a telescope with an 8-meter lens, which is the largest ever. And it also contains a 3,200 megapixel camera. And what that means is that it's going to map the sky. So what the intent of it is over a 10-year period to see the changes in the sky. So every night, it's literally going to take a video of what the sky looks like. And if you can imagine all that information, I think they're looking at 60 petabytes a year, and I'm sure they've way underestimated that. So what they're thinking about, and this already is out of date, this nightly transfer rate of 20 to 40 terabytes, I mean, it's not even up yet, and they're already saying that's probably going to double. That this is going to use 200 gig fibers from Chile, and then fiber connection back to the main data center is going to be at NCSA down at Champaign. So just the challenge of getting this data from a hilltop in Chile, and it had to be built someplace where there wasn't a lot of ambient lights. Just the challenge of getting that there, getting it to a central data center, and then people getting access to this data, both the raw data and processed data, is a huge networking challenge. So some of our other programs within my division, we see networking. I mean, I wanted to give those examples as kind of just an overview that it's really fundamental to do science and scientific cyber infrastructure. So our campus networking upgrade program, we're trying to get every campus to at least 10 gig for smaller schools, 100 gig plus for larger schools. We do a lot of international networking. We provide, because of that global nature of science, we do a lot of network connections. We've just awarded a bunch of them to link US research with peer networks in other parts of the world, to Asia, to Japan, to South America, all over. and we're doing a transoceanic experimental trial right now. Just some other examples. This is kind of a list of things that we do. So one of the big things, and actually the expert on this is Nick, who spoke earlier on SDN, about the science DMZ concept, and you should ask him because he's much more hands-on than I am. But one of the interesting things that's come about as we get this data-intensive science and these challenges is how do you best get from your typical campus network. In many ways, it's like an enterprise network. You have your LAN and your desktop and then your WAN. But a scientist who needs access to 10 gigs at one time doesn't, it's not really optimal to go through that traditional campus network. So what Energy and Sciences Network at the Department of Energy figured out is, I call it a firewall bypass, but it's essentially this science DMZ. And the whole point is to get huge science data flows and get them directly from where you need to use that data out of the campus and back. So how do you get around all the crap that's in between your desktop or your cluster and the big science flows? And what we try to encourage through our network upgrades is you need to put in a science DMZ and show us how you optimize your network by using this. And here we have it, the science DMZ. So if this is just your generic template of a science DMZ, and basically it includes a data transfer node, some kind of switch router or combination device, and the border router. And just all sorts of interesting setups as to how you can use this to get around your campus or your enterprise network to optimize your flows. And that's really taken off. I think other places, other agencies and certainly other places are starting to look at this concept of how to optimize flow, big flows. It's just an award map of our connections that range generally 10 gig up to 100 gig and where we've given awards in the past 2 years. I'm going to just talk a little bit about, so in our particular area, what I'm focusing on today, although the NSF funds lots of interesting research, our fundamental driver is science and science flows. So we have lots of awards about software-defined networking. What we heard for years is SDN is in search of a problem. It's just something that's out there. Well, there's significant problems in data transfers for science, and these are some of them. So it's used at the University of Maryland, University of Washington for physics, particle physics. They're a big consumer. Again, the LHC in Geneva sends lots and lots of data. Astronomy, getting from Hawaii to the mainland, 80 gigs and they're starting to fill that already. And then LSST, which I spoke about. I just picked a few examples, and I won't talk too much. You can kind of read that. But basically for, we look at a couple things at the NSF. One is the intellectual merit. So we want to look at what does this do to improve science. We also look at the broader impact. So when we give an award, we want to look at, it doesn't just advance that researcher on that campus and what he can do to optimize the network. We also look at what's the broader impact. Can the community be a benefit? Can it help teach STEM in any better way? Can society benefit? Can maybe a local museum or a library or somebody else use that connection? So these are just some ways in which that's helped. University of Houston, their big driver was genomics. They have a big medical complex there. So they were, it affected researchers by multiple orders of magnitude. These guys, maybe they had a gig before, now they have 100 gigs. And we see a few different scientific disciplines that are really pushing the envelope. Physics, genomics, and astronomy tend to be the three big ones. This one I brought up, I thought this was a really interesting, for us the proposal came in, it was very interesting. This Northwest Indian College, it's actually between 3 states, and they serve, I want to say it's a population of like 20,000 people in the area. And they had absolutely really pitiful connectivity. So they had a very basic science DMZ, and they just wanted, like a 1 gig connection. But what the broader impact is that there's this huge area of the Northwest where American Indian students had broader access to resources at other institutions. Other institutions had access to these scientific catalogs of things they were cataloging up there. So just to show that networking, we really try to use it for not just really interesting, pushing the envelope things, but also to reach out to students who wouldn't otherwise get access. This is just an example of, so NDN, if you're not familiar with what that is, it's called Named Data Networking. That's part of this overall program called Future Internet Architecture. It's stuff that we can't even envision, but lots of smart people are trying to envision what the new internet's going to look like. And named data networking, the theory is you're not going to use an IP address anymore. You're going to say it's all going to be based around content. So I want to access, X content, and instead of specifying a place where it is, the network will find it for you. So again, lots of smart people are trying to figure that out, but they're trying to migrate workflows using that named data networking versus IP addressing. And that's about a 10-year project to figure out what we're going to do for the next internet. This is my own solicitation, cybersecurity innovation. So there's a few focus areas, secure architecture design. One of the points is we're trying to get away from funding point solutions, a better firewall, a better IDS. Clearly that isn't working with all the hacks we're getting. So we're trying to look at what's the sum total of the architecture, the end-to-end architecture. Don't think of it as a perimeter. Think of the data provenance. So where's the data coming from, and two, what's that chain of custody for that data, especially if you're trying to do climate change and you're basing your results on somebody else's results, but you're not sure where they came from. That could have a big impact if your scientific results, you don't know the origin of it, and then you're making policy decisions. So that data provenance, that's a big concept for us. It's used a lot for financial firms. They really know where all that data comes from. There's a great chain of custody. Not so much for the science workflow. In the past, people said nobody cares about scientific data, but these days when you're making major policy changes due to them, people are starting to care more. And SDN is a huge, huge theme for us. We're really looking for concrete cases of SDN usage, and we're seeing more of it. I want to talk a little bit about secure and trustworthy cyberspace. That's a huge project I'm involved in. It's now an $80 million project. It supports fundamental advances in security. So it's everything from privacy to better crypto, better hardware, better supply chain. We're trying to put a lot of money into figuring out better security. Oops, somehow went backwards. So the scope of it is to cast a wide net and let better ideas surface. So within that program, there's other programs where we try to transition research into practice. The research that we see can be very, very ethereal and very researchy. And we know as operators that is sometimes very divorced from the reality of how a router and a switch and an IDS actually works. So sometimes the research goes nowhere except into papers, and our job is to figure out how we can transition some of that into reality. So these are some of the funding areas. You can see it spans everything. Social networking is a huge one. How to figure out everything from fake Yelp reviews and Sybils to cryptographic theory. This is a really interesting program called STARS. We love cute acronyms, but I'll show you the diagram on the next page. And what STARS is trying to do is, this is an area that I wasn't familiar with, but it's really looking at semiconductors and the security model there. And I'll bring this up. So this is it may be a little hard to read this, but long story short, what we're trying to do, in addition to the regular design weaknesses that can lead to security vulnerabilities like side channels, backdoors, hardware is very vulnerable to counterfeiting and tampering. So that's all kind of known, and that causes a chip to, of course, not perform as intended. But when you look at the actual flow of fabrication, manufacturing, what I didn't realize is, in your ARM chip in your phone, that chip, the function in those chips is all made up of this software intellectual property. And Apple buys it from hundreds of different vendors, and they have a lock on certain IP that does certain things to your phone. But when they sell you that package, it does a whole lot more than, let's just say, dim the light on your iPhone. It does 10 or 12 different things. Apple buys it to do one thing, but you can't really guarantee those other 5 or 10 things aren't turned off. And when you buy 100 or 200 of these software packages, there's really not a way that they know how all the software interacts. And in addition, in the manufacturing process, someone brought up, well, if you just put something in there that, you burn the chip in so that you know when it's been tested and it's authorized. That gets done so early in the process, that's not a guaranteed way. So really the vulnerability is where you're mapping the software onto the chip and onto the hardware. That is two completely separate processes. So there's just major issues there, and that's a place where we're trying to look for what can we do for security assurance along the whole semiconductor chain in order to thwart these threats. And that's a consortium. We're actually working with all the major chip manufacturers and ISPs on this. They're actually putting money because they need to figure it out as well. Just an example of the softer side, kind of social behavior. We do a lot of research in economics of spam and social media analytics. That's really important. So some of the things we're looking at is, for this project in particular, detect, classify, measure, and track the formation, development, and spread of topics in cyber attacker communications. So this particular researcher, he spends a lot of time on the darknet, and he looks at how people form these connections. So he'll look at how hackers or how different people, how they literally form those social connections and how they translate that into reality. So we do kind of the softer side of research as well. Shell, this is really hard to read, I know. This is one of the things that we transitioned to practice, and actually it's in a few Fortune 500 companies now. And in a nutshell, in near real time, in under a second, it is able to detect malware, put it in a container, and see whether it's truly malware or not. And the user, I mean, it's almost at line rate speed where the user doesn't even see it. It detects it so quickly. So it's in an appliance, but it doesn't feel like it goes through an appliance. But the researcher was acutely aware of what needed to be done and had a very, really wanted to take it from research to practice. This is another one that's, again, some folks in the room are familiar with. It's being transitioned more to Fortune 20 kind of like a really big company using Bro IDS. It's a very flexible, very, I would say hard to configure, but time intensive to configure intrusion detection system. And this really bridges that gap between research and kind of real network operations. And this is its 20th year that it's been in development. And it can run at 100 gig. So it's very useful for a lot of our supercomputing centers. And it's fundamentally different because it doesn't just detect anomalies, it actually figures out what your network, kind of how your network normally runs, the pace of your network, what comes across your network, and that's how it figures out the anomalies. It's not based on some database somebody else came up with. Just some small projects we're working on. Our PKI, we're thinking about, are people going to use it? SDN security. These are kind of 2-year just projects to see if they work out. Just wanted to mention, we also fund the scholarship for service. 2 to 3 final years of study. Because cybersecurity expertise is so hard to get, NSF puts a lot of money into this program where you're virtually guaranteed a job. Over 93% go to work for the federal government, the others work for contractors, and that's to, you get your last 2 years of school for free as long as you are majoring in something that's security related. So I always find that really interesting. Just a couple last slides. We're deeply involved in, I did not put up here Internet of Things because that's what it's going to be called next year. But it's called Cyber Physical Systems now, and that spans everything from transport, smart health, anything that's a thing that a light bulb, anything we're calling cyber physical systems. And really the security in those smart systems is a concern for us, especially when they talk to each other. So this is another area where we're getting into. So the cyber physical system security, we're working on it with Department of Transportation, with National Institutes of Health. If you think about Department of Transportation, they're really interested in autonomous vehicles, and we helped fund the Google card. So if you think about platooning of vehicles that people aren't driving, how do you solve that challenge of, GM, they also buy chips that maybe are not secure. So if someone wants to hack a car, which is fairly easy these days, and they're in a nice line of the highway and one gets hacked, that's a huge issue for us. So transportation's interested, NIH is interested from kind of your Fitbit and smart devices. And that is all I had. I just wanted to give an overview. I don't know if anybody has questions or.
How far along is the... Here, I'll use my human megaphone trick. How far along is the Shell OS thing, the inline...
It's in production.
It's in production.
It's in production.
Because I have one quick question.
Sure.
So you mentioned a lot of really interesting research that's being happening, but if you're not a researcher and if you do want to somehow get involved, I guess what would be the process, whether it's some sort of collaboration between the company you work for or your personal time interest? I guess how would you bridge that step?
Yeah, that's an interesting question. So it depends on the program, but for example, the Secure and Trustworthy Cyberspace, anybody can apply for it. So we give out a lot of grants to 1 or 2 person companies who have a really interesting idea, or you don't have to be a researcher to apply for that. You can be just a guy with an interesting idea. We have partnerships with Intel and big companies like Intel, Cisco, Symantec. But for many, if not most of these, not the campus networking, but for most of these, you don't have to be a university researcher to apply for them. Okay.